this example is also asking us to verify this trigonometric identity. So we've got 2 secant squared alpha equals 1 over 1 minus sine alpha plus 1 over 1 plus sine alpha. So I'm going to leave, again, this side over here only has a secant squared alpha on it and a 2. I'm going to leave that alone. That's pretty happy, that's pretty basic. I'm going to just focus on this fraction side because it's going to be easier to get these fractions all combined to simplify down to secant squared alpha rather than trying to figure out how to write secant squared alpha into this. That's not pleasant. We're not going to try to do it. So we need to think of our fraction rules here. So when we're adding and subtracting fractions, we have to have a common denominator or a shortcut way. This still gets you a common denominator, but it's a shortcut way. It's called a lot of people call it the butterfly method. You could also call it the cross multiply method, whatever, floats your boat. So if you are adding or subtracting fractions, you cross multiply. Oh, that is thick. Okay. You cross multiply, so you get a d, and then you do plus or minus, and then cross multiply the other way, b, c, all over b times d. Okay, so just to prove my point here, 2/3 plus, let's say I did 1/6, all right? A common denominator here could be 6, or a common denominator here could be 18. So if we did 18 as our common denominator, we would multiply this fraction, we'd multiply top and bottom by 6, and if we did it over here, we'd multiply top and bottom by 3, okay? And I would get 12 over 18 plus 3 over 18. Or I could do the cross multiplying, and I could get 2 times 6, which is 12, plus 3 times 1, which is 3, all over 3 times 6, which is 18. And if I put these into one fraction, I would get the exact same thing. So that is why this method works, and I highly recommend it. It doesn't get you maybe the least common denominator, but it does get you a common denominator, and that's all you need. So going back over here, so now we're going to use that method that we just talked about, and I'm going to have 2 secant squared alpha equals 1 times 1 plus sine alpha. So I'll have 1 plus sine alpha plus 1 times 1 minus sine alpha, which is just 1 minus sine alpha. And I'm putting them in parentheses because if this was a minus sign, then I'd have to distribute that minus through both of those. So it just keeps everything straight, but a plus sign, it doesn't really matter too much. Now I'm going to multiply the bottoms. I'm actually going to come over here and multiply the bottoms out over here. So 1 minus sine alpha times 1 plus sine alpha. Okay, so I need to use, I don't know if you guys were taught the FOIL method. Some people call it the FOIL, or basically I need to distribute the 1 through this other set, and I need to distribute negative sine alpha through this other set. So how I'm going to do that is I'm going to multiply the 1 through. So I'm going to get 1 plus sine alpha. Then I'm going to multiply negative sine alpha through, and I'm going to get minus sine alpha minus sine squared alpha, because sine alpha times sine alpha is sine squared alpha, and it's a negative times a positive, so it's a negative. Sine alpha minus sine alpha, that goes away, and I end up with 1 minus sine squared alpha. Okay? So we'll put that back into our problem. 1 minus sine squared alpha. Cool. And we'll start simplifying. So I'll have 2 secant squared alpha equals, now 1 plus 1, I get 2. And then sine alpha plus negative sine alpha, those go away. That equals 0. So now I have 2 over 1 minus sine squared alpha. Okay. So now I have 2 secant squared alpha equals 2 over. So now I need to think, okay, 1 minus sine squared alpha can I combine that? If you've got a 1 plus or minus some other trig function that's squared, you're probably looking at your Pythagorean identities. So if we go look at our trig sheet, we'll look for sine squared alphas and 1s. So our fundamental Pythagorean identity, sine squared alpha plus cosine squared alpha equals 1. If I bring sine squared alpha over to the other side, I would get cosine squared alpha equals 1 minus sine squared alpha. So 1 minus sine squared alpha can be rewritten as cosine squared alpha. So that would give me 2 over cosine squared alpha. So now I have 2 secant squared alpha equals 2 times 1 over cosine squared alpha. I just broke up this fraction. Just remember, if I do 2 over 1, I recombine it, I'd have 2 times 1 over cosine squared alpha. So I just broke up the fraction. Again, a lot of fraction rules with these. And so then I'd ultimately end up with 2 secant squared alpha equals 2. Now 1 over cosine squared alpha, well, 1 over cosine is secant. So 1 over cosine squared is secant squared alpha. And we have just proven or verified this trig identity.